All right, we're going to discuss percent dissociation. Percent dissociation, which I abbreviate as percent dissociation, really revolves around only weak acids. They really never calculate percent dissociation of a weak base. We already know what strong acids are. We already know what strong bases are. Strong acids and strong bases dissociate 100%. Therefore, calculating the actual percent dissociation would only revolve around weak acids. So this is only going to pertain to weak acids. All right, percent dissociation, weak acids only. What is it? It is a quantitative determination of the percentage of ionization an acid undergoes. In other words, what percent of hydronium ion forms from a particular acid. A weak acid compared to another weak acid at the same concentration will depend on the K. The smaller the K value, the weaker the acid, the smaller the percent ionization. Because of course the smaller the K means less products. The larger the K, the stronger the acid, the larger the percent ionization, because a large K means lots of products. If you're dealing with a dilute acid compared to a more concentrated acid, a dilute acid will have an increased percent ionization due to Le Chatelier's principle. So you're either comparing a weak to another weak at the same concentration, or a weak acid compared to itself at different concentrations. All right, the computation. For example, this is a generic dissociation of an acid. Here is your generic acid, hydrogen attached to some other substance, a binary from the halogens or an oxyanion in water. Dual arrow indicates weak. Hydronium ion gets created plus the conjugate base. Percent dissociation is going to be the concentration of your hydronium ion, which from ice table math or ice table calculations is your X divided by your initial concentration of your acid, which is usually given in the problem, times 100. So this is an example. We're going to calculate the percent dissociation of a 1 molar hydrofluoric acid. What we have in the problem is we have our initial concentration of the hydrofluoric acid, but what we're missing is the hydronium ion, and I need the hydronium ion. So the first thing we have to do is calculate hydronium. If you're already familiar with ice table math and how to set it up. Again, as always, it's going to be very set up your ice table. There are no coefficients to do it. It's always going to the right. Reactants are always losing a quantity. Products are always gaining a quantity. It's going to be K, in this case Ka, is going to be equal to 1.00 minus X IX hydronium ion concentration at equilibrium, and of course the fluoride ion concentration is going to be 0.027 molar. My percent dissociation, therefore, is going to be the hydronium ion concentration at equilibrium divided by the initial concentration of the acid, which is given in the problem, times 100%. My percent dissociation for this example is 2.7%. You've got 2.7% hydronium out of that acid. Not a lot, but that's what percent dissociation does. Now, put your podcast on pause. I want you to do this problem on your own, and then I will show you the